In case you've forgotten, in the month that I've been away, I do distributed computing. And distributed computing is kind of a very wide field. It talks about many types of distributed systems, anything from multiple threads running on one CPU all the way to LAN networks like we see here, and newer kind of networks like mobile robots are walking around trying to talk to each other and accomplish some goal. But the common thing to all of these, like the reason that we sort of study them as one field, is that in this class of system, really the most expensive thing in the computation is the communication between the participants. In fact, this is to such a degree that when we model these systems, we typically just completely ignore the cost of local computation. We don't charge anything for local computation steps, and we only charge for communication, whatever communication may happen to be in your system. So if we're talking about threads running on the same CPU, then communication means touching data that another thread also wants to touch. If we're talking about a system that communicates by radio, then it's sending messages over radio. So whatever communication may be, that's the bottleneck. Lower bounds in distributed computing have typically, for many years, taken a sort of very all or nothing approach. Usually, if two processes or machines or robots or whatever have not communicated with each other, so one has not, let's say, sent a message to the other one, then we assume that the other one knows nothing about the first one. And this is true, right? If communication is not gone across, then you don't know what my state is. But the other side of the coin is usually in these lower bounds, we're very pessimistic, and we assume that if there has been communication, then in fact everything about the other guy is known to you. So usually we assume that the protocol just sends the entire state. And actually a lot of early protocols were like this. So if you look, for example, at the first ever protocol that solves consensus with malicious faults, what this protocol does, every process takes its entire state up to now, everything it's received, who it heard it from, and so on. So this exponentially growing tree, and that's what you send in every round. And it was amazing enough that, in fact, this was even solvable. So amazing that people were willing to settle for these exponential protocols. But as time goes on and we refine our understanding, it becomes more interesting to actually do a more fine-grained analysis and look at the cost of computation, how many bits you actually need to send. And this has grown kind of very popular in the community in recent years. And for this kind of question, it's very natural to use communication complexity. So just to remind everyone here who already knows this, what is...
To be fair, after this flooding protocol for consensus, they worried about...
Absolutely.
Even in the 80s, and they had polynomial size.
No, that's true.
Communication.
That's true, but a lot of times if you look at these early protocols, even when they're saying polynomial, what they're measuring is the number of messages, not necessarily the size of the messages. Yeah, so this particular one was polynomial. But a lot of times, bit complexity was not a thing that people cared about. And it's sort of growing more and more interesting. OK, so just a quick review of what is communication complexity. This is the model that Yao came up with in the late 70s. So it's a very abstract model of communication. We have two players, Alice and Bob. Each one of them gets a private input that only they know. And their goal is to compute some joint function. Their inputs, and naturally, in order to do this, they have to talk to each other. And the only thing we care about is how many bits do they need to send. So as in distributed computing, local computation is totally for free. I only care about how many bits Alice and Bob send to each other. And lower bounds that I'm going to prove today will be mostly by reduction from two-party communication complexity. So let me just give you sort of a broad overview. Communication complexity has been very useful to prove distributed lower bounds. But there are some differences in the kind of things that we care about, and as a result, in the kind of questions that we ask. So for example, the complexity measure that we care about in distributed computing usually is the number of rounds. So I'm going to give you a limited budget of bits that you can send per round, and now I care about how many rounds you need to do that. Whereas communication complexity usually cares about the total number of bits that you needed to send. So of course, if you have a very high lower bound on the total number of bits, and I tell you you only get to send 5 bits per round, then you get a lower bound on the number of rounds. But sometimes the problem doesn't have a high total lower bound on the total number of bits, and yet it still takes a lot of interaction. So this is interesting. But today the problems that I'll talk about really do have a large total communication. That's the approach that we'll take. The type of problems that we care about in distributed computing, often decision problems, but very often search problems like elect a leader in the network, find one spanning tree out of many possible spanning trees, and so on. In communication complexity, there are many interesting search problems, but often the focus is on decision. Many lower bound techniques work well for decision problems and so on, so I think this is also an interesting space to look at. And the input, which is maybe the biggest difference, when you're working with distributed systems, the input is very local. So the machines typically only know their small part of the network or the input. We call this number in hand input. And I put this asterisk here because actually the class of problems I'm going to talk about today is not quite totally local. We'll see that in a minute. But if you tell classical complexity people multi-party communication complexity, they immediately assume you're talking about number on forehead, which is the model where every player gets to see everyone else's input and not their own input. And that's useful for lower bounds on circuit complexity and so on. So that's another big difference, although recently there have been many great results in this arena as well. Okay, so the class of problems I want to talk to you about today is distributed graph property testing. So here's the setup. We are going to work with a shared blackboard model, so we have a number of players. When they talk to each other, they write messages on the board, and everyone gets to see this for free. It's also interesting to look at a model where, so this sort of corresponds to broadcast communication, like in a radio network when I send a message and everyone sees it. It's also interesting to think about unicast communication where I can send different messages to different people. But it turns out that if you want to analyze that model, it's very hard, and it's as hard as proving circuit lower bounds. And if there's time, I'll tell you a little bit about this at the end. So for now, we're going to assume just broadcast. When I say something, everyone knows it. The players go in simultaneous rounds, and in every round, each player gets to write B bits on the board, where B is some parameter. And I care about the number of rounds that they're going to need. And the input is going to be an undirected graph on n vertices, and every vertex is associated with a player. So player 1 is identified with vertex 1 in the graph. And the input to each player will be the edges adjacent to this vertex. So why did I say not quite number in hand? Because the graph is undirected. So every edge is known to both of its endpoints. So we have a little bit of input sharing, much, much less than we have in typical number on forehead. All right, and the goal is to determine if the input graph satisfies some property. Let me just remark that this type of thing has been looked at by many people. In particular, it seems to be interesting to look at the simultaneous complexity of these problems. So you only get one shot. You have to send something. A referee gets to see all the messages and has to decide. That's kind of easier to give lower bounds for than what I'm going to do today. The particular problem I'll talk about today is subgraph detection. We have this input graph. We have a fixed subgraph H, which is constant size, not growing with n, although many of the results also do carry over if H is growing. And I want you to tell me if H appears as a subgraph in your input. Okay, the trivial upper bound on any problem in this model. You only have n bits of input, your edges. And if you send them in chunks of b bits each, then after n over b rounds, everyone knows the entire graph, and we're done. So we'll see that this is actually tight for some subgraph detection problems, but not all. Any questions so far?
Does everybody need to know the answer?
Everybody needs to know the answer, but it's actually, since we're working with shared blackboard, we might as well assume that only one guy needs to know it, and then he can write it on the board. That's for free almost. It matters, actually, yes. I will give lower bounds that are almost always for randomized. In one case, we're not able to get a randomized lower bound, and I think that's an interesting open problem. Yeah, but the randomness model here is private randomness. It doesn't make a lot of sense to assume public randomness for this model. Okay, so I'm going to reduce from the following two problems, which I assume everyone knows. The first one is disjointness. Alice and Bob each get a subset of the elements from 1 to n, and I want them to tell me if there's any intersection. A very famous and celebrated lower bound says that even for randomized algorithms, you cannot solve this problem with less than order n bits, which is of course optimal because you can always just send the set over and be done with it. The other problem, so this is very useful for exact lower bounds. Is there an intersection or is there no intersection? When we want to get an approximate lower bound on approximation algorithms, it's very useful to reduce from another problem, gap Hamming distance. Here the inputs are interpreted as vectors, binary vectors on n bits. I want the players to determine for some gap parameter g, is the Hamming distance between x and y bigger than half plus g or smaller than half minus g. So g is a gap here. Of course, the bigger g is, the easier this becomes. And this was actually studied for a long time. It wasn't an easy lower bound to show, but Chakrabarty and Regev settled it in 2010, and they showed that this is actually really hard, even for sort of moderately large gaps. So even when the gap goes as high as square root n, it's still linearly hard. Okay. So here's a lower bound on a particular subgraph detection problem detecting 5 cycles. I want to claim that if you give me, not induced, just exists as a subgraph. Yeah. So I want to claim that if you give me a fast algorithm, which takes r rounds in the distributed model and detects 5 cycles, then I can solve disjointness on n squared elements in a time that grows linearly with r. And that will tell us that r cannot be too small. So how do reductions like this usually go? We're going to take the inputs x and y to Alice and Bob. From these, we're going to have to construct some sort of input graph that we can run our distributed algorithm on. Then Alice and Bob will need to simulate together the run of the distributed algorithm, hopefully without a lot of communication between them so that the reduction will be cheap. From the answer to 5-cycle detection, they should know if the sets are disjoint or not. So the input sets, I'll interpret them as ordered pairs. And in the end, after you simulate the algorithm, the answer should tell you the answer to disjointness. Right? So this is a pretty simple reduction, and here it is. This is sort of a part of the graph that will always be there regardless of the input to Alice and Bob. They'll always construct a graph that has these edges. So we have 5 groups of nodes, and the bottom 2 are connected just directly in a perfect matching. And in the top, we also have 2 perfect matchings like this. Now comes the input to Alice and Bob, and they add the following edges. So if Alice got the element ij, she's going to put in an edge from I on top to j on bottom. And Bob is going to do the opposite. If he got ij, he will put an edge from I on bottom to j on top. Okay, so when does a cycle appear? If and only if there's some element that both of them got, and then you can go down and also go back up. Right? So how do we simulate the algorithm? This is actually a part that you always need to be very careful about, because sometimes you have an amazing reduction, but it just turns out that the simulation cost is too high. So you have to be a little bit careful about it. So here, Alice is going to simulate everything to the left of this line here. Bob will simulate everything to the right. So each one of them has a linear number of nodes to simulate.
So I just wonder if you had C4 instead of C5.
Wait a few minutes and we'll get there. There is a reason I started with C5, and that's exactly what you're thinking about. Okay, but for now, C5. In order to simulate each round, so assume they are already sort of locally storing the state of each node that they need to simulate. The first round is trivial. There is no input yet, so they can do this. If they have done it up to some point, then each player knows what message its node wants to send. okay? And it can send this information over to the other player. How many bits are being sent in total? Order of NB, right? One message per each node being simulated. Yeah, each one of these guys. Yeah, so the total overall cost of the entire simulation is the number of rounds times NB. We know that this had better be at least n squared. So we get a lower bound of n over b for the number of rounds, and this matches the trivial algorithm.
That warned us that it's an easy job.
I did.
I know. Okay, you did that.
Oh, you were in sort of high gear. Yeah, nothing I'm going to say today is technically challenging. So let me warn you in advance of this fact. And in fact, you know, what I'm going to talk about today, it leaves more open problems actually than it settles. So we have tight results, but only for maybe even toy cases. And I wanted to tell you about this because I think it's an interesting arena to develop. Okay, but this lower bound happens to be both easy and tight, which I don't know what you guys think about it.
The
But
best of all worlds.
right. Okay, what if I wanted, instead of exactly detecting a cycle, if I wanted to approximate the number of cycles? Well, it's pretty easy. In this reduction, the number of cycles was exactly the size of the intersection, right? And the size of the intersection is related to the Hamming distance, like this. So if we know the sizes of the input sets, which it's very easy, it's cheap to exchange, so we might as well assume that we know them, then by telling me how many cycles you found, I also know the gap, the Hamming distance between the vectors. So just by going through the same reduction, we get this lower bound on approximating the number of cycles. Sorry? No, alpha here is like, yeah, so this is, it becomes constant if alpha is constant, right? This is not a great lower bound. In fact, I don't know if it's tight. I suspect that it isn't. There's two things wrong with it.
What about, the approximation between 0 and 1?
Right.
Yeah.
So this is one of two things I don't like about this lower bound. First of all, it doesn't seem it degrades probably too quickly. Second, arguably, this is not the lower bound that we would want, because gap Hamming distance is hard around n over 2. So the hardness you get here also has roughly that number of cycles initially, right? You're not distinguishing between no cycles and a lot of cycles. So arguably, the lower bound that we would want to prove is tell me if the graph has no cycles or if it has a lot of cycles, and this doesn't do that. It does not address it.
But you already know that it's hard to differentiate between no cycle and one cycle.
Yes.
So this is what you proved, right?
Yes, because set disjointness is also hard if you only restrict the intersection to be either 1 or nothing. Yeah. So 0 or 1 I can distinguish, but how about 0 or epsilon n? So for deterministic, it stays hard because we know that disjointness is also hard in this regime, but yeah, I don't know. I didn't think about this too much. Maybe it's easy to get, but you know, just by reducing from gap Hamming distance, you don't get it. And there's another sort of other way to look at approximation, which would also be a nice lower bound, I think, to show. When we talk about property testing, usually we don't talk about this kind of thing. The question we ask is, does your graph have the property, or is your graph far from having the property? Do you need to add or take away a lot of edges in order for it to have the property? And this is totally not what we're doing here.
So between 0 and epsilon n, if you just think about the construction you had before, but with graphs on square root n, so you have in vertices, you kind of take a blow up of this thing, so that every single cycle will correspond to many of them, because I replace every set by complete bipartite graph.
Yeah.
And then still you are kind of doing the disjointness maybe on sets of size square root n, so you should be able to get a lower bound of square root n.
It sounds, yeah, it makes sense. Yeah. This is not something that we've really thought about. This paper actually doesn't mention anything about approximation. It's only the exact results. Yeah, but like I said, I think probably the more interesting direction to go in is to ask about distance, like edit distance of the graph in some sense from a graph that has the property. Okay, so back to Avi's question. Why did I start from 5? So it's obvious why I didn't start from 1. It's pretty obvious why I didn't start from 2. There's a good reason I didn't start from 3, and we'll see it soon. And let's address 4. So if we try to do the same kind of reduction, we have something like this. What's wrong with this? Not you. Sorry? Yeah, exactly. So we might have for a cycle, a rectangle appearing just in one player's side, completely independently of the other guy's input. So this reduction doesn't work. How do we fix it? Instead of taking a complete bipartite graph here, take some graph which has no 4 cycles, right? And we know how to construct these. And then the edges of this graph will be the elements of said disjointness, right? Instead of here having a complete bipartite graph whose edges were the elements, now it will be something smaller. And I'm losing, but this will again be tight. So the graph can be C4 free while still having n to the 3/2 edges, and this is the lower bound that we end up with. And it turns out that this is tight. Okay, but you can start to see the reason why we don't know the full answer to this, because we know how to do it for even cycles and for odd cycles. We know how to give a lower bound, which is not tight probably, for complete bipartite subgraphs.
It's tight again because of the extrema, because if you're
Exactly. Yeah, I'll show the algorithm. There is this relation to extremal, to Turán numbers, which is again not technically hard at all, right? But for more complicated types of graphs, we don't know how to do this construction in such a way that you don't get a subgraph in one guy's input. Okay, what about 3 cycles or triangles? So this is where things get, in my opinion, interesting. The trivial upper bound is again n over b. We suspect that this is tight. We don't know how to prove it yet, but we know how to prove it for deterministic algorithms. Almost, not quite. Okay, why did the approach that I detailed so far, it's actually not going to give us anything for triangles. And in fact, no 2-party black box reduction where all you can do is simulate the algorithm and not like look at its insides is not going to give you anything non-trivial about triangles, because if you try to construct this kind of reduction, every triangle, 2 of its vertices are simulated by one player. And this player can see the entire triangle, and it can tell if this triangle is there or not without talking to the other guy. Okay, so this is where the input sharing comes back to bite us, and that's sort of why I think it's interesting. So if input sharing is the problem, we can address it by using a model of communication complexity that features this input sharing. So we can get a lower bound on this by working with number on forehead. This is what we do. Specifically, we work with just 3-party number on forehead. Sure, again, everyone has seen this, but here we have a 3rd player, Charlie. Every player gets to see the input that is written on the foreheads of the other 2 players, but not its own input. And in this model as well, set disjointness has been extensively studied. The problem is still defined as before. Is there an element that all the players got in their input? So here's our reduction now. For the reduction, I'm going to use a class of very cool graphs that were constructed by Wusa and Savaredi. So they construct a tripartite graph, which has the following properties. First of all, it's fairly balanced. So the parts are of size n, and n over 2. Adds up to more than n, but forgive me for that. And more interestingly, it has many, many triangles, almost n² triangles, but every edge belongs to exactly one triangle. Okay, so this is a very cool construction. All right, this is just, I'll give you a second to take a look at this. The important property is many triangles, but edges are uniquely associated with triangles. So the reduction will be from number on forehead disjointness, where every triangle is an element. of set disjointness. And this is the reduction. Once you think of using number on forehead, this reduction is, again, pretty easy. So we have Alice, Bob, and Charlie. They will each be simulating one part of this tripartite graph. When they receive their inputs, x, y, and z, here are the edges that they'll put in the graph. So for every edge, we can, as I said, we associate it with a unique triangle. And the subgraph we construct, so if some edge, some triangle is written on Charlie's forehead, then Alice and Bob will put between themselves the edge that corresponds to this triangle. Okay? It's important that both of them see Charlie's input because both of them need to agree on whether this edge is there or not. Okay, and the same for the other guys. If something is on Alice's forehead, we put this edge. And if something's on Bob's forehead, we put this edge. Okay, and again, if you tried to do this but you weren't working with number on forehead, the thing that would go wrong is it could be that there is a node here that thinks it has an edge to a node here, but the other guy thinks the edge doesn't exist. Okay, so that doesn't work in our model. All right. So the a triangle appears here if and only if there is some triangle that is written on everybody's foreheads, and then all the corresponding edges are put in, and really we have the triangle in the graph. The cost of the simulation, as before, is linear. So the round complexity of triangle detection is however hard it is to solve disjointness with almost n squared elements divided by nb. Right, so what do we actually get? Unfortunately, not too much, because we don't know the true answer for three-party disjointness in the number on forehead. For randomized algorithms, the best that we know right now is square root the number of elements. Unfortunately, this exactly gives us nothing, because we start with less than n squared. We're dividing by n, so we get less than 1. But for deterministic algorithms, as we were writing this paper, Anoop and Amir proved their linear lower bound for deterministic algorithms. So we're proud to be the first application of this lower bound. So here it's a linear lower bound. And what we get is almost n squared divided by nb. I apologize for b becoming sometimes non-capital. And we get a nearly tight lower bound for deterministic triangle detection. And I've spoken to Anoop about this problem. It looks like we might be losing something by having this three-party reduction. So conceivably, if you take their lower bound, which they simplified Scherstoff's randomized lower bound, and you actually work with the problem that we're talking about, you might be able to squeeze out this gap. But this is open.
Anything for players? I don't remember this new result.
Yeah, the new result.
Any constant.
Yeah, any constant, it's 2 to the k. Or actually, it might be 2 to the 2k.
N over 2.
Yeah. And 4 to the k, thanks, yeah. Yeah, so sort of in general, the reason I find this interesting is that I'm interested in this sort of no man's land between things we can address with two-party reductions and areas where two parties don't really capture what's going on in your distributed system because it's not really two parties. So this is one of these things. All right, so let me give you the upper graph on subgraph detection. And again, it is an easy upper bound. And it has to do with Turán numbers. And this is a very natural connection. So the Turán number on n vertices and a subgraph H is just the maximum number of edges that you can put in a graph on n vertices and still not have H as a subgraph. These are not understood very well even today. We know that for triangles, or in fact for any odd length cycle, you can just take the complete bipartite graph and that'll do. So it's n squared over 4. But even for the 4 cycle, we already don't know the exact answer. We know that it's roughly n to the 3 halves. And in general, for any even cycle, we know it's bounded by this, but it's conjectured not to actually be that high. And if you go to other types of graphs, it's a pretty open area. And the connection to our problem here is pretty natural. If your graph doesn't contain H as a subgraph, then it cannot have that many edges, and we're going to use that. And here's how we use it. So if your graph happens to not have H as a subgraph, it doesn't have a total large number of edges, which also means that there have to be a lot of nodes with a small degree. How small? At least half of them have a degree which is no more than 2 times the Turán number over n, right? Because that's the average degree. So these nodes, we can dispose of them pretty quickly. Just take this many rounds for them to send you all of their edges, right? And then take them out of the graph, because now we know everything we need to know about them. Okay, so we eliminate half the nodes in the graph. And now we can recurse. We have to be a little bit careful about the recursion, which I'll address this in a minute. But overall, there will be log n rounds. In each one, we send something like this. We spend sort of something like this in order to discover the edges of a lot of nodes, and then we'll be done because we know the entire graph, right? A few things can go wrong here. What if you don't have enough nodes with a small degree? Then you know that the graph is too dense, and you should immediately stop, right? What if the graph happens to be not H-free, but still sparse? Well, we're recovering all of it, so in the end, we can just look at it and discover. All right? One thing we have to be careful about, after we recurse, we end up with a subgraph, which has fewer vertices. It's still H-free, of course. We didn't add anything. But the average degree is now this creature, right? It's not necessarily the same as it was before. Fortunately, it's easy to show that for any subgraph that you might encounter in this process, this average degree doesn't go much above the original average degree of the graph. Why is that? So let me pick some number n double prime, which is however many vertices you have now, times 2 to the s, and I want to place it between n and n over 2. All right, so essentially, I'm taking the gap between n and n prime and approximating it by 2 to the s.
Say n double prime equals n prime.
Yeah. Fix s such that, you know, pick the closest thing you can here in the range between n and n over 2. And then check how large s needs to be. Sorry? Yeah. Here.
Oh, this is times.
Oh, I'm sorry.
Oh, this was period.
Oh, I apologize. Bad PowerPoint. Yeah, okay, so it's clear. Just put it, you know, somewhere in between n and n over 2, and then approximate it. So notice that what is this average degree here? Here I'm just writing it out. This should, yeah, so I'm doing nothing at all, right? Just multiplying and dividing. And now, what is this here? So if I look at the Turán number for anything times n, it's never less than the anything times the Turán number of n, because I can always take here 2 to the s disjoint copies of the extremal graph for n prime, right? And it will have 2 to the s times the edges. Okay, so what is this? It's exactly the Turán number for n double prime over n double prime. N double prime is not more than n, so also its Turán number is not more than the Turán number for n. And here it's not less than n over 2, so we're done.
In fact, what happens is that the average degree strictly reduces.
Right.
And so I think that you don't need the extra log really, because it's a power you have a convergence here.
We're not sure about this. We don't think this is tight. We think you can get rid of 1 log. Actually, we thought we had an algorithm that does that.
If the graph H contains the cycles, then the Turán number is a power already. It's not linear.
Mm.
And then it will reduce, I think.
Yeah. So it's probably true, but I don't want to commit to it in this celebrated form. All right, but this is the algorithm. So we've shown that we can detect the presence of any subgraph in something that corresponds to its Turán number over NB. We think that this is the right answer. And we know that this is the right answer for 4 cycles, because the Turán number for 4 cycles is n to the 3/2. So that's exactly what our lower bound says. It's also the right answer for any odd cycle, again, n over b. But we don't know about other types of graphs because we're missing the lower bounds for them.
Graphs are the hardest.
For triangles, you didn't.
For triangles, we only know it for deterministic algorithms, yeah. And this is a deterministic algorithm.
And also there is, I mean, this is when you interpret the tilde, or no, not in terms of logarithms, but in terms of to the square root laws. Is also okay.
No, I would be happy to get it out of there. But it seems like it's asking for a lot from this particular reduction. So
even for K4, you don't know.
Even for, no, for 4 we have only a log factor. Oh, K4 we do know it. For K4 it's a very easy lower bound. I didn't show it here, but it's very hard. So it's n over b again.
So what's the first clique you don't know it for?
No, but probably you know for all of them because it just
All the
gets,
cliques.
harder and harder. And the Turán number follows them.
Yeah, so if you want the reduction for cliques, take the thing we had for cycles, add all the cross edges.
So sorry, complete bipartite graph.
Complete bipartite graphs, we have a lower bound. It's more complicated and it doesn't match this.
Well, you don't know what the Turán number is for complete bipartite.
Also, we don't know it, yeah. And by the way, a cute trick which you can do, this is maybe a little weird. I'm giving you an algorithm, but we don't really know how long it's going to take. You don't have to know. You can guess it. You have to be a little bit clever and sort of subsample a graph with the right density corresponding to your guess, but you can do it. Okay, but
So sometimes you can show that this is tight even though you don't know.
Yes.
Because you have construction.
yeah, it adds some log factors for the guesses, but yeah. Okay. Since I do have some time, let me tell you a little bit about this other model that I mentioned, where it's the same as the model we're thinking about now, except you get to send a different message to each one of your neighbors in each round. Okay, so informally, like the total number of bits going across is pretty much the same because in the shared Blackboard model, I got to send B bits to everybody, so everybody was still receiving.
Still asking something?
Oh,
So-
sure.
So what is the simplest graph for which you don't know?
Complete bipartite. Your triangle,
Because
first
so
triangle.
complete bipartite, you don't know
Case 3, 3.
because although
Because
so even case 3,
yeah, we have a lower bound which doesn't match this.
because you cannot use
Yeah. So again, you need to take an extremal graph and you need to sort of embed it in your reduction. We were able to do it and get something, but it doesn't match this. Right. In triangles, I think
for
it's
C4 it works just because it works.
yes, exactly. Yeah. So I would say triangles if you like number on forehead type questions, and complete bipartite otherwise, because that you probably can get by reduction from 2 parties. All right.
Is there a good example where, or maybe you mentioned it, where there's no 2-party reduction, or to use the 3-party?
Right, so I think it's interesting to even ask these meta questions sometimes, like can any reduction at all give you what you want here? And for 3-party number on forehead, I don't really know how to prove it, but I would hazard a guess that maybe you cannot get a tight lower bound for randomized triangle detection from 3-party number on forehead. But this ties into what you believe about disjointness in 3-party number on forehead. Right, other questions about this? All right, so I wanted to tell you a little bit about this because it's a result of a collaboration here at IAS last year. This is the version of the model where again, so you get to send different B bits to everybody instead of having to send the same B bits to everybody. And this raises the computation power so much that we can't hope to prove anything. Maybe you guys can. This model has been pretty widely studied in the distributed community. It's accepted as a reasonable model to talk about. It's known that you can do things really, really fast in this model. So you can sort a lot of numbers quickly. You can find minimum spanning trees. In fact, even this triangle detection problem, it was raised as a candidate hard problem to prove lower bounds in this model, which we show you cannot do. And the guys who worked on it actually said, well, we wanted to prove a lower bound, but in the end, too bad, we found an algorithm. So, but the best algorithm here is actually only n to the 1/3, so it's not that great. So what we showed in this paper is that if you're able to prove lower bounds on this model, which is called the Congested Clique, then you get lower bounds on bounded depth circuits with unbounded fan-in and with a restricted class of gates, not any type of gate, but reasonable gates. So I'll show you how this goes. Again, it's easy. In this talk, I'll just talk about ACC circuits. The nice property of ACC gates, which is the simpleness that we need, is that if you take the gate and you look at its inputs and you give a subset of the inputs to a number of players, then if we want to compute the value of the gate, we can have each player send us a short summary of what it saw. It doesn't need to tell us the entire input, right? So if your gates are AND gates, OR gates, majority gates, mod C gates, you know, arbitrary functions, no, but anything we are likely to care about, yes. Oh, yeah? I don't know. What if it's a disjointness gate? Okay. Then maybe I'm not sure what you mean by symmetric. Okay, I see. Oh, sorry. I was thinking of a different notion of symmetric, sorry. Okay. So yeah, any symmetric function.
So this is 0.
Yeah. We also have, you know, so everything I see here for ACC, we also get the same kind of implication. So here I'm going to show that if you can give me a lower bound for the congested clique, you'll be proving a new ACC lower bound. We make a similar statement for TC0 with unweighted gates. All right, so fix a function. It'll have n squared inputs, and it'll be Boolean, although it doesn't necessarily need to be. And give me a circuit that computes it, which can use AND gates, OR gates, and mod M gates. And let D be the depth of the circuit. You know, what I'm going to care about is the number of wires in the circuit. So let's denote that by n squared times S, and we're going to care about how big S needs to be. Okay, so n squared is just to read the input. And it can have unbounded fan-in and fan-out. Okay, I'm going to give you a fast protocol for the congested clique. It'll have roughly the depth, number of rounds, and small bandwidth. And it will compute F. So eventually everybody will know the value of F. Okay, so I also have to tell you where the input goes. Pretty much everybody gets n bits of the input. So this is why it's n squared. We have n players, each one gets n bits. All right. So what you might think to do, we have this circuit, take each layer of the circuit simulated by one round of the algorithm. That's exactly what we're going to do. We're going to assign every gate to a player who will have to collect sort of the inputs to this gate and then compute the answer and send it on to everybody who needs it for the next layer. And the goal is to have good load balancing so that we don't need a lot of communication between the players, right? So we don't want to, for example, give all the gates to one guy. It would be very easy for him to compute, but not very efficient. So let's say that a gate is heavy if its total fan-in is this big, right? So this is starting to be problematic for us because you need to collect a lot of things in your input in order to compute it.
Now, just to see where you're going, you just prove where you say that superlinear low bounds.
So yes, essentially what we get from this is that if you are able to prove a very modest, even super constant lower bound for the congested clique, then you're proving better bounds than we know about the number of wires for ACC. Not super linear, even slightly super constant.
No, no, I mean the implication.
Oh, yes, 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 yes.
Something that we don't know, but it's not that.
It's this n lambda function, which goes as iterated log. Yeah.
What is it? I mean, there is only S gates in the. What is it?
No.
N squared times S.
Okay.
Yeah, this is the number of wires, but you can have. Okay, but for heavy gates, there cannot be that many of them because each one of them takes up n s wires, so there's no more than n heavy gates, and we can just take each heavy gate, give it to one player. So now we know that this player must collect n s inputs, but that's it for the heavy gates. What about the light gates? It turns out that you can just be greedy about them and just assign them to the players sort of greedily in such a way that no player gets a total degree of n times s. This is trivial. Okay, and remember that this works because the total degree of the circuit is not more than n squared s. All right, so here's how we evaluate the circuit. For the light gates, we just send out all the values individually. You know, if I computed a gate and you need the value, I'm going to send you that value. For the heavy gates, since we have a total in degree of no more than ns, this is a very well-balanced sort of routing that we need to do here. And it turns out, and it's easy to see, that you can do it in a constant number of rounds. So here, every player has s things it might need to send to every other player, roughly speaking, so you can do this in a balanced way. And for the heavy gates, we use this niceness of the gates that you don't need to send me really all the inputs for the gate. You can just send me a summary, a short summary.
So summary is n per play.
It's actually less than that. It's like log,
Sorry, log.
yeah, log n plus s. Okay, so I'm sorry I'm glossing over the details, you know, but this is pretty much what you would expect it to be. And what do we get from this? So here's the implication for ACC. This is the best lower bound that we know on the number of wires for bounded depth ACC. For depth 2, it's n log n, and then it becomes very, very bad very, very quickly. And what we get from this is that, you know, chop this n out. If you can prove a lower bound on the number of rounds, which grows this quickly, the inverse of this, sorry, then you're proving new lower bounds for the congested clique.
All
So
these lower bounds are basically by graph theory.
yes,
Just in super constant.
exactly.
Of this depth, so you would need to bypass this. You need to go beyond this.
Exactly. But you know, if you were able to do that, you get new ACC lower bounds.
Yeah.
Yeah.
I meant that getting this,
Oh, yes.
These are interesting because they would require going outside
Of super concentrated lower bounds, yeah. Right, so some people in the community were not pleased to hear about this barrier, but it's there. And what is very easy to get is a non-explicit lower bound, which you get just like with any circuit. Even for a random function, yeah, it's very hard to compute. Almost.
Is there a barrier or a new technique for proving lower bounds?
So in some sense, yes, this distributed model is cute and it's nice to work with, but mostly for algorithms.
Yeah, so if you got an algorithm,
Yeah.
you
Other way around.
yeah, the other way around, yeah.
Yeah.
I don't know, it may not really make any sense, but what if you don't need to know you don't have to agree and get it right, the value of the function all the time. Just with some, whatever measure of closeness. These techniques that say
So in some sense, if you can find someone who's close, so let's say everybody has a different opinion, but one of them is right, and you can somehow identify that, then it reduces immediately to this case. In general, I don't know. So if you have everybody coming up with their own answer, and you have no idea which one of them is right, and it's hard to detect, then this probably doesn't apply.
Actually, what is the lower bound for random function?
For a random function?
Yes, the n players, it says n bits.
Yeah, so it's n minus log n over this parameter b. It's exactly the same that you would get with the circuits. Okay, and we also have a similar result for TC0, but it's quantitatively less impressive. It's a barrier at log n, because we have a better understanding right now of TC0 lower bounds. All right, so that's all I wanted to tell you about. Really, this leaves more open questions than answered questions at this point. For instance, I think a construction for general graphs might be interesting to see, combinatorially interesting. Again, I mentioned this true property test, a reduction.
For the lower,
Yeah.
for getting the lower.
Yeah. So I probably shouldn't say construction, reduction for general graphs.
What is the best lower bound that you have for any graph?
Nothing. We don't have anything.
So nothing in terms of the Turán number or something, or
Yeah.
Turán number subgraphs.
No, we were not able to get that. We thought, you know,
don't have a super constant lower bound
for
arbitrary fixed graph.
Yeah.
For any fixed graph.
other, there's the ones that I mentioned
Yeah,
in the
no,
talk,
but-
but other than them, no.
Oh, yeah.
Yeah.
All graphs of size 10. There may be a graph of size 10 for which we don't know.
Yes, in fact, there is.
I mean,
The complete,
Case list.
Yeah.
You don't have any lower bound.
we have a lower bound, but it's not tight.
No,
Oh,
no,
I see. No, in general, yeah, everything except for cycles, cliques, which are very easy, and complete bipartite graphs, we don't know anything about in terms of lower bound.
graphs that, so trees or something, if the Turán number is linear, then it's indeed the upper bound is,
Yeah,
you still have the logarithm there.
for trees, it's very easy. The
it's
problem is
constant,
easy.
okay.
I think it's logarithmic.
It's still logarithm.
I think so, but
That's
I'm
the
not
truth.
sure.
I mean, the logarithm would follow from the general upper bound because
In some sense, the logarithm is for telling you the edge. So I think it should be there.
so it's not constant.
Yeah, I don't know how to do it in constant. And I think our lower bound.
For some trees, it's constant, right? A star of size 10 is
Yes.
constant because one vertex would know it.
So let me be conservative in my answer. For trees, I think we have no lower bound because it seems to be somewhere around the constant to log range, and our algorithm is log. If you wanted to prove a lower bound of log, you might be running into questions of like set disjointness with small sets and so on, which might not be good because you can solve set disjointness with small sets linearly. Okay, and in general, there's many other problems that are maybe even more interesting, like testing for connectivity, which is a really interesting problem. And in fact, you can't get a lower bound here by any k party number in hand reduction for any k. So you really have to work with the actual model. And this is something that Mark and I are working on.
But you can't get a reduction to number in hand, but what about?
What about number on forehead? I don't know. I don't know. All right, so in general, this is a class of problems that I mentioned 2 years ago in a talk here, and I still feel that it's interesting, but some progress has been made. Everything I talked about today is communication over a complete network. Either you broadcast and everyone gets it, or you send messages to everyone. But often in distributed computing, we care about communication over some arbitrary network graph. So what happens? In some sense, this should be much harder because now you sort of need to repeat information in order to get it where you want it to go. So if k is the number of nodes in the graph and n is the size of the input, can we prove lower bounds which are more than what you would get for the complete graph, which is nk? So there's been some really nice work in this area. And in fact, we do have powerful lower bounds for some problems. We don't have a general understanding of what problems become harder and why. And also, one sort of weakness from my perspective with these things is that n and k are decoupled here. So the input has nothing to do with the network graph. It's just some input. And for many distributed problems, the input is the network graph. So that's, as far as I know, no one has said anything about.
N is the total size of the input.
No, n bits per player.
N bits per player. So if it's 1 bit per player, then the quadratic lower bound,
Yes.
which is type.
For, yeah. But here's a candidate problem. So I want you to compute all pairs exact shortest path on the input, on this graph, which you're communicating over.
So that everyone knows its own.
You need to know in the end, for every other node, I'm going to make this very hard for you. Every other node, you need to tell me what is your distance.
Yeah, for you.
Yes. So this seems like a good candidate to prove this type of lower bound on, but we don't have it yet. Yep, and that's all I have. Thank you.